Hey YouTube, this is David from PEslayer.com again. We're looking at a structural question for the PE Civil Breadth exam. It seems like every practice exam that I've looked at has a question similar to this, where it will list several shapes and it will give you a loading and it will ask you which of those shapes is best in that particular loading. Now these questions are more theoretical. We're not going to go through any math. And that's how you want it to be. You want to know the theory behind this so that you're not trying to do any crazy math equations on the PE, wasting all sorts of time. So we'll go through this one. It says, which of the shapes shown would have the greatest buckling capacity, assuming they all have the same cross-sectional area, wall thicknesses, and are all made from the exact same material. The drawings are not to scale. So this is one pet peeve of mine is, and I'm not sure if they do it on purpose, but it says that the drawings are not to scale, and it's obvious. I mean, it's good that it says that because it's not. And it says to assume the cross-sectional areas are the same, and if you look at them, they're clearly not the same. So we just have to kind of, remember that all these cross-sectional areas are supposed to be the same. Let's see, so we have to know a little bit about buckling. When you calculate the buckling load, all of these shapes are gonna buckle about, I guess most of these shapes will be able to buckle about one of two axes. So for example, on this I shape, normally under normal conditions, it is going to buckle about the weak axis. So if we're looking at the cross section, it'll buckle out this way, unless it's braced in such a way that it's braced against that buckling, but maybe it has a very long unbraced length about the other axis. It could buckle that way, but that would be rare. But I guess the thing to know about this shape is there is a weak axis and a strong axis. Okay. Looking at the square, this is like a square tube. Okay. Now, in this case, if we drew orthogonal axes, it would have the same moment of inertia, and it would have the same radius of gyration, and those are kind of the properties that you use to calculate buckling. It would have the same moment of inertia and radius of gyration about each of the two different orthogonal axes. But you could draw another axis in, maybe from this corner to this corner diagonally, and that would have a different moment of inertia and a different radius of gyration. So although it's not obvious that this has different radius of gyration and moment of inertia, it does if you draw the axes at angles. Okay, so in that, if you think about it like that, then this shape does have a weak axis and does have a strong axis. So if it buckles, it would definitely go out this way, or it would go out this way, but it's not going to buckle like out diagonally like that. Okay. Looking at the circle, you could draw an axis in any orientation, up and down, left and right, or diagonally, and it's always going to have the same moment of inertia and always going to have the same radius of gyration, which means there is no weak axis in the circle and there is no strong axis. It is equally likely to buckle in any different direction. Okay, and the circle, because of that, it's like there's no extra material in the circle. It's as light, it's as efficient as it can be. So if it has the same cross-sectional area as all of these, then that means it is going to have the greatest buckling capacity. I'm not even going to look at the angle because it seems like anyone with half a brain would know that the angle is not going to be the most efficient at carrying compressive load. But yeah, we're going to go with the round tube final answer. This has been David with PEslayer.com. We'll see you next time.